Post-tensioning stresses in simple members. The outline of this presentation includes distribution of stresses in members that are not restrained, then stress distribution in members that are restrained, some examples of stress distribution. Then I go and talk about load balancing. Balanced loads, so to say. I give some examples of balanced loads. This is something we would be using when we use load balancing design. Now let us start with stresses. If you have a section and a force is acting at the location shown, now whether it is from post-tensioning or otherwise, there will be bending moment about the two axes X and Y, and at any point, say B, the distribution of actions will be an axial force and a bending moment about one of the axes and a bending moment about the other axis. This is no different from a section having a force on it. Here I feel a little bit uneasy to talk about post-tensioning because this strictly is showing the application of a concentrated force at a point on the cross-section. But if you have a post-tensioning tendon that passes through the section, the force in the tendon is not entirely transferred to the section. Tendon transfers its force at the anchorage. The precompression is where it is, tendon is stressed and anchored. At a cross-section along the length of a tendon, like the one I am showing here, it is only the friction between the tendon and its sheathing that is transferred to the section. This is the reality. Nonetheless, if you look in the literature and common practice, the common belief is that if you have a tendon at the location shown in A, at the point B, there will be actions as here. This is valid for the anchorage, but anyway, this is the way it is done. Now, the bending moments are force times eccentricity, and you have the axial, and the stress at any point B here is given by the simple beam formula where plane sections are assumed plane. So there is a component from moment about X, a component from moment about Y, ZX and ZY are the section moduli associated with B. Now, if you have a member shown in A which is fully free, and you have a post-tensioning tendon passing through its centroid, the force is exerted at the anchorage, but along the length, due to the curvature of the tendon, you have, so to say, side forces. The combination of the two results in a uniform stress for a tendon that passes through the centroid and is not connected to anywhere else. There will be a uniform precompression, and there will be a shortening at here. There will be no bending. the distribution of stress from PT tendon will be uniform precompression along the entire length of the member, no bending of the member. The member will shorten as shown here, but will not bend. Now, if you have a situation, the member is supported along its length in addition to the far end. It is free between B and C. Between here and here, the member is free. So the tendon passes through the centroid of the member along its entire length. The free segment between B and C, will be under axial load and uniform precompression. The deformation between B and C will be shortening without bending. Sorry, between B and C is here and here. Here it will shorten but will not bend. Now, the constraint at C results in reactions V and H. The reactions at C lead to moment in segment at CD. There will be bending moment here because of these reactions. The moment along CD, will result in out of plane bending. So from here to here, you will have bending, moment, and of course change in curvature. From here to here, you will have axial shortening. Obviously, the rotation at this point will have a body rotation here too. Now, we are continuing on stress distribution. The figure in A shows the elevation of a member, and here is the plan of the member. In the elevation, the tendon passes through the centroidal axis. Being located at the centroid, the distribution of stress through the depth will be uniform, as indicated here. Now, figure B shows the same member in plan. In plan, the tendon does not follow the centroid. In plan. The off-center results in a non-uniform distribution. So you have uniform distribution through the depth, but non-uniform along the horizontal axis. Now, this is a popular example I have seen in a number of locations where you have this bent bar and a post-tensioning tendon that passes through the centroid of the member through the hollow tube and is anchored at the far ends. The question is, whether the member bend? Will the arms of the member bend? Never mind breaking, whether it will bend. And what is the distribution of stress along here? Now, the member will not bend because everywhere the tendon is centroid and the distribution of stress is uniform as section AA, which is representative of a section along the arm. the distribution of the force acting at the centroid will result in uniform stress. So you have uniform stress here, all along at these distributions. The force is at centroid, so the stress will be uniform. There is no moment on the section, hence there will be no bending. At the knee of the member, here, shown in BB, the three forces shown will be in equilibrium. Again, not bending, they are congruent and neutralize one another. In summary, the member will not bend, but its arms will shorten from the compression. That should be compression imparted by the tendon. Now I am going to move into a different topic, and that is the topic of balanced loads, which you may encounter in your post-tensioning designs. There are three methods to design a post-tensioned member. One of the methods is called a straight method, then there is load balancing method, and then there is comprehensive method. Presentation 8 of this series explains the difference between these methods and gives references. Two of these methods, namely the straight method and load balancing, require that the post-tensioning forces to be extracted from the member and accounted for separately. You have dead load, you have live load. Also, in two of these schemes, you will also have post-tensioning force. And the post-tensioning force is referred to generally as balance loads. And the next couple of slides are going to talk about this. Now, if you have a parabolic tendon, the lateral force here from a tendon in shape of parabola can be closely approximated as uniform load. So a lot of engineers, in particular in the past, where computer application was not common, profile for tendons consisted of parabolic segments so that the force will be uniform. That will be easy to do the calculation, easier than otherwise. The extracted PT tendon forces is referred to as balance load. For ease of computation, when computers and analysis design software were not available, tendons were assumed in shape of simple or compound parabola to conclude with simple balance load distributions. Now here I have an example of a 3-span member with a tendon which goes from one end to the end. In this tendon is shown in A. It's made up of parabolic segments with low points at midspan and high points over the support. So this is the tendon shape. The up and down forces exerted by this tendon to the structure is shown here. We analyze the structure if we use a balanced loading design scheme or a straight method, like what is shown at the bottom. Two concentrated loads here and up and down forces on the member. B, shows the forces from the tendon, and C are the tendon forces on the member. Now, what I just showed you in the previous slide was the common practice, but we have instances where the design requires that the post-tensioning be somewhat different from simple or compound parabola, like this example that I show here. You have a straight tendon below the member's centroid in figure A. The balance load is the action of the tendon on the member, shown in B, is represented by a compressive force here at the anchors, and a bending moment at each end. Force times eccentricity will cause a bending moment at each end, and that bending moment results in this distribution that I have. So to analyze this member at the top, you will be using what I have shown here at the bottom as contribution of tendon. Now this is another example where we have a non-prismatic member with a tendon consisting of two straight segments, a segment here and a segment there. The balance load is the action of the tendon on the member. It is shown in B. This is the balance load. Now, the balance load consists of three concentrated forces: P at the anchors, these are two of them, and F at the kink here. So these three forces are the forces that you will apply to this structure when you want to investigate the impact of post-tensioning. The impact is governed by these three forces. Now this is another example where I have a tapered member in elevation, but of uniform thickness. Post-tensioning tendon is straight and is anchored at the centroid at the end. Acted at the centroid, so it does not apply a moment here at the centroid. The balance load for the arrangement consists of the axial force. The axial force acts here and here, and its distribution is constant. It's a constant axial force, but the axial force having different varying eccentricity with respect to each of the sections will cause a different moment. There will be a bending moment along the member resulting from the eccentricity. The bending moment at each section, in this case, is P, the force, times its distance from the centroid of the section. Now, in summary, what did we cover? We talked about distribution of stress in unrestrained members, and then distribution of stress in restrained members, in unrestrained members, and restrained members. And unrestrained members, you have a bending moment which adds to the axial. And then I gave you some examples of the distribution. Then we talked about balance loads and examples of balance loads. That brings me to the conclusion of this presentation. Thank you.